All right. Good morning, everyone. I hope you had a good weekend. So we'll get started. Let me share with you my screen here on a PowerPoint. All right. So let me just put into the full screen mode. And yeah, again, if you just text me something in the chat, say hi, good morning, or hello, I'll track that later and then take attendance like that. Okay. All right. So at the same time, I will just get started on the lecture part. Again, a couple of reminders. So homework 8 is due tomorrow by midnight. And then the next homework assignment will be due Monday next week. Okay. And then on Wednesday next week, we'll have our exam 3. So exam 3 should be just covering the topics of magnetism and induction. Okay. And then maybe I think there will be something also about Maxwell equation, the electromagnetism, okay, in the chapter 24. So we should be able to cover 24 by this chapter 24 by this week. Okay. I should be available most of the time this afternoon and also most of the day tomorrow. So in case if you need help on your homework number 8, you can use the Zoom link I post on Moodle for the office hour. You can click on that one, and I will be notified. I'll join you a few minutes later. Okay. I don't know if it works out as smoothly. A couple of times I asked my wife to test that with me. Actually, I got email quite very soon after she joined. So if you have been waiting for quite a few minutes, if you still didn't see me joining online, just send me an email. Okay, so I think email system works pretty reliable at this point. Okay, so I'm suspecting that Zoom is not as reliable. I haven't got issue with it, but because sometimes when you guys join the meeting for the lecture, then about say 5 hours later, I got email say someone is waiting for me in the classroom. So apparently sometimes there's a delay on the Zoom on the classroom, but I haven't having an issue on my office hour link yet. Okay, but just in case, okay, if that happens, if you've been waiting for me for quite a few minutes, I still do not join you, then you send me an email. Okay, I'll be coming over then. All right. So these are the some of the reminders items here. Now we'll get started on the lecture part here. All right. So last time we talked about motional EMF. So meaning if you have a loop inside a magnetic field, and then part of loop can be moving. So then in that case, you actually can create EMF in the circuit, are called motional EMF, because that's due to the movement of a certain part of the circuit. Okay, and on the figure shows here, we can kind of determine what will be the current inside the loop given the direction of the rod that is moving either to the right or to the left. Okay, and then you can determine also the magnetic force the rod will be experiencing because now the rod will have a current going through it. So there should be magnetic field on the rod. Okay, there should be magnetic force on the right by the magnetic field. Okay, you can use right hand rule. So 2 right hand rules you can practice here. Right hand rule 1, it is used to determine the direction of magnetic force for current. And then right hand rule 2 is used to determine the direction of the magnetic field produced by a current. Okay, and then we mentioned that, or we actually discussed this when the mechanical power by if you just pull in the rod by using an external force, so that gives you the rod a mechanical power. Okay, so if we look at the expression of that compared to the expression of the electric power consumed by the circuit, you realize they are the same expression. So that tells you that mechanical power you give to the rod is going to be equal to the electrical power consumed by the circuit. Okay, so in that way, you actually generate electricity by moving the rod. Okay, and that's the mechanism of most of the electric generators. So for electric generator, it takes in mechanical work in different kinds of the forms. For example, you can have steam generator. Okay, so there's quite a few example of steam generator, like nuclear power plant and then coal mine or coal power plant, like that. Okay, and then there's other kind of like hydraulic or the using the water potential difference. Okay, so that doesn't involve steam, but basically an electric generator will take in mechanical energy, okay, and then convert it to electricity. Okay, so the figure here shows the schematic drawing of a electric generator look like. Okay, so for electric generator, typically the electricity generated should be either a sine function or cosine function. Okay, that is due to the angle the normal direction makes with the of the loop makes with the magnetic field. So it's either sine function or cosine function. So then for the electric potential, it would have a maximum value, which is given by MBA omega. Okay, N is number of turns coils you have, B is the magnetic field, A is the area of the coil, omega is the angular frequency. Okay. Now, on the other hand, electric motor is the other ways. It's exactly opposite of electric generator. Okay, so it actually takes the electric power in and then converted that into mechanical power. Okay, so if you have toy car or other kind of device powered by electric motor, then that's what happens. Okay, so it's a similar device. It just works the other way around, the reverse way. Okay, to the electric generator. All right. Now, in that case, for any electric motor, because the coil is also moving just as electric generator would have, so then there will be back EMF, which is the EMF generated due to the movement of the coil. So that's in the opposite direction of the input electricity. Okay, so that's a concept you want to get familiarized with. But that's how much we need to know here. All right. And then we also talk about transformer, electric transformer last time. So basically, you could have a step up transformer or a step down transformer, or you can have combination of them. So in the example shown in the figure, where how the electricity is being delivered from power plant to the household. Okay, so it involves both step up motors and or step up transformer and step down transformers. Okay, and then these are the equations you want to use when you are solving a problem with transformers. Okay, so basically the power on both sides of transformers should be equal to each other. Okay, and then you can use that the other two equations to determine the ratios given the number of turns or coils on both sides. Okay, to the voltage and then also to the currents. All right. We also talk about electrical safety. This is one more feature added to the ones, the measures you can take for electrical safety previously when we talk about electricity. So in this case, for appliance, the case of appliance should be proper grounded. Okay, so then that is an additional safety layer so that people don't get shot due to the wear out of the appliance case. Okay. All right, so today we'll be checking on the new section here on induction. So we have been talking about induction for a couple of lectures. So basically, if you have a coil, if you have current going through the coils, so then there will be magnetic field generate. Okay, so this is the case. So you can have a coil. So typically, you would have a solenoid. So that means many turns or coils here in a circuit. So what happens here? So now think about this one as analog to the a capacitor in the circuit. Okay. So if you have resistor, if you have a solenoid, say in this case, then there's a power supply in this circuit given by the battery. So once you close the switch, there will be power, or there will be electric current going through the coil, okay? So then there will be magnetic field generated, all right? Now, the factor that the current here actually increases with time, okay? So it's not like the current is not changing because there's this coil over here, all right? So it acts some delay in the stabilizing the current, okay? So it takes time because this guy is here. Because you can imagine, so when this is just closed, so the current, before it's closed, the current should be 0, okay? Once this is closed, the current start to increase. All right, now if you have increase in current, that means the magnetic field generated here will be changing, all right? So because of that, now we know this is a coil over here, so then there's an induced EMF if there's changing in the B field, magnetic field, because the magnetic field is changing, then flux going through the coil is changing, okay? So in that case, then there will be induced EMF generated in the coil. Now with them, according to Lenz's law, induced EMF will be opposed to the cause of the changing of the flux. So then if this is increasing, so then there will be EMF induced here, which creates a current, induced current that's in the opposite direction of this driving current, okay? This increasing current. So then the current will be in the opposite direction, or this is equivalent to have a induced EMF, okay? You can imagine like treat this as a battery, okay? So then this battery should have the opposite um, potential differences here. So that means if this is positive, then positive is against that one, okay? So then overall, it reduces the overall power potential on the circuit, okay? So this is what happens. So when you have coil there or solenoid there, then the factor is the induced EMF, okay? It's in the opposite direction of that, so we can also call it back EMF, just like the ones in the electric motor, okay? But then gradually, this current will increase and then reach a stable value, then it's no longer changing, okay? So then this one will be disappearing because now at a certain point later, there's no change in current, then this guy disappear, okay? So there wouldn't be an induced EMF because there's no change, so there will be no induced EMF, okay? So this is what happens when you have a coil in the circuit, okay? And this phenomenon we call it induction, okay? Because the solenoid or the coil will have ability to kind of reduce the change, okay? So then we call this as induction because it's due to the solenoid. And so this induced EMF in the circuit is equal to or proportional to the current because that's the it's actually due to the change in flux, but then change in flux is due to change in current, okay? So then definition of induction, L, we use L for induction, it's the factor that the proportional, the constant proportionality constant to relate the induced EMF to the current changing, okay? So epsilon, it can be determined by either this one or this equation here, or equal to this one, the one on the rightmost here. So epsilon is equal to L delta I delta T. Okay, you take the absolute values. So then L, you can solve for it, you can set up this because epsilon is equal to this, it's also equal to this. So then you can just take these two expressions, set them equal to each other, you can solve for L, okay? So solving for L is going to be equal to the number of turns coils you have in a solenoid and divided by delta phi over delta I, okay? So that's what you can, how you can solve for L, okay? For induction L, it has SI unit of Henry or using symbol H, okay? 1H is equal to 1 Henry, equivalent to 1 voltage times second divided by amps, okay? So that comes from here. okay, amps from here, and then flux will have volts times second, okay, due to this equation here, okay, because this is in volt, this is in second, so delta phi should be volts times second, okay. So let's take a look. When we talk about solenoid, so we say the magnetic field produced by the solenoid should be equal to mu naught Ni. Okay, so this is what we have before a couple of lectures back, and then where this small n is equal to capital N divided by L, the length of the solenoid. All right, so we can calculate if there are n turns of coils there, then the flux, magnetic flux, should be equal to MBA. All right. Now B is equal to this guy. You take B in here. All right. And so then M, you can take the expression from here. Capital N should be equal to small n times L. Okay. So then n, you in this expression you do the square for n because there's one n coming here, one n coming from there. Okay. And mu naught is coming down from there, I is coming down from here, L is from here, A is there. Okay, so this is magnetic flux. All right. So then, according to the definition for or the equation we saw in the previous slides for solving for inductance for solenoid, we can do phi divided by I. All right. Now in this case, we have already included M here, so we don't want to repeat. Okay. So in the equation we showed earlier, let me just go here. So this is referred to the flux for one coil, okay? Now, in this case, we have all the flux through n turns of coils in here. So then we don't have to do a capital N again, okay? So this is what we have. If you do 5M divided by I, then you do this guy divided by I. So then just I goes away. Then you would have L equal to mu 0 M square A times L. Okay, so this is the expression for induction of a solenoid. All right. So when the solenoid is used in a circuit, it's also called an inductor. Okay, so then easier you can relate the induction to an inductor by using this name instead of solenoid. Okay. All right. Now let's take a look for the energy stored in an inductor or solenoid. Okay, so we know that induced EMF, okay, can be expressed in this relationship. Okay, epsilon, but we are not taking the absolute value, so then this is equal to minus L delta I delta T. According to Lenz's law, the minus sign should come here. Okay. Now, if we use a loop rule for this circuit, so we can start from one point. We can probably start anything from here. So then you cross the battery from negative to positive, the voltage increases. You cross the resistor, it decreases. Okay, and then across this guy, the voltage across this one is given by this expression. Okay, so then coming back to the original starting point, you should have the voltage change equal to 0. All right. Now, if we manipulate this a little bit by multiply both sides by the current I, all right, so then we have this one, epsilon 0 times I minus I squared minus Li delta T equal to 0. Okay, so if we look at those three terms, we know that if we do voltage multiplied by current, that term will give you power, right? Because power is equal to V times I, is also equal to I squared times R. All right, so then these two terms, they are both in the dimension of power. So then this term should be also in the dimension of power, okay? So then the power in the inductor or solenoid should be equal to this guy, okay? Li delta T, all right? So if we know the power stored in the inductor, the expression, then we can calculate what's the energy stored in the inductor, okay? Because power is defined as energy divided by T, time T, all right? To do that, if we do the energy divided by delta T, so if we use U as energy, okay, so you can use E as energy, okay, either way, but in this case, we use delta U. So then you can see that delta U over delta T is equal to Li delta I over delta T. So delta T and delta T will cancel out. So then you will have this expression. Okay. Now, to calculate, so this is change in energy, okay? The rate of energy changing that gives you power. So then to calculate what's the energy, okay? In this case, we would have to use the calculus knowledge to derive this equation, okay? But you can ignore these two steps, okay? This just tells you how the energy is being determined. So at the end, this is the expression you need to know, okay? So energy stored in a solenoid in the form of magnetic field is equal to 1/2 L I squared, okay? I is the current in the solenoid, L is the inductance of the solenoid or the inductor. Okay, so you can see it's proportional to the current squared, okay? Now, let's take a closer look on the energy stored in the solenoid, okay? If we look at the magnetic field produced by a solenoid, because it's many turns of coils, then there's current, so there will be magnetic field, okay? So again, it's mu naught N times I. And then for inductance of solenoid, we just derive this expression a couple of slides back that is equal to mu naught N squared A times L, okay? So then, therefore, if we look at this expression here, all right? So this is the one we had in the previous slides. The energy in the solenoid is 1/2 L I squared. Now L, we can take this expression down. And then I, you'll just have to divide both sides by mu naught M. So then I equal to B over mu naught M, okay? So this is I. So you do square of that. Now, if you check the terms over here, okay, there's a square here. If you square here, then N square goes away, okay? And then mu naught here, there should be mu naught squared down here. So you cancel one mu naught with one mu naught remaining. So at the end, you will have B squared A times L, okay? B, because you squared it, and then AL, and then 2 here in the denominator. So energy, then if you express in terms of the magnetic field, can be equal to magnetic field squared times A times L divided by 2 mu naught, okay? However, if you look at this, A times L, A is the cross-sectional area, L is the length, okay? So then these two multiply will give the volume of the solenoid, okay? So this is energy in the solenoid or the inductor is equal to P squared AL divided by 2 mu naught, okay? So if we replace AL as V, the voltage, as the volume, and then we do the energy divided by the volume, then that will give us the energy density, okay? So energy density is equal to, if we use small mu, overall energy is capital U, M divided by volume, then you end up with, because this is times B squared times volume divided by 2 mu naught, this is volume. So then you will have mu energy density equals to B squared divided by 2 mu naught, okay? Now, let's take a look back when we talk about electric field. So when we say for a capacitor, it actually stores energy in the form of electric field, right? So in this case, a solenoid or inductor actually stores energy in the form of magnetic field, okay? And then it's equal to this guy in terms of magnetic field, okay? Now let's have a quick review on the energy stored in a capacitor. All right, so energy is equal to Q times average V, or 1/2 QV, and either equal to 1/2 CV squared or Q squared divided by 2C. All right, and then when we did the math over there, if we replace V as E times D, C is given by this equation. So at the end, this is what we have for the energy is equal to epsilon 0 E squared. Okay, you can see here again we have field squared divided by 2, and then times A times D. So again, this gives you the volume. If we do energy divided by volume, then at the end, energy by a capacitor in the form of electric field is equal to epsilon 0 E squared divided by 2. Okay, so if you compare the two expressions, let me write it down on my paper here so you can see the two expressions, okay? So for electric field energy, by a capacitor, this is equal to epsilon 0 E squared divided by 2. E is the field, okay? Now for the magnetic field, energy stored in the magnetic field by the solenoid or inductor, it was B squared, or it was, B squared divided by 2 mu naught, okay? So you can see these two expressions, they are very similar to each other. Energy stored in the electric field should be proportional to the field square, okay? Multiplied by a constant number, all right, which is epsilon 0 divided by 2. Epsilon is 8.85 times 10 to the minus 12. This guy, energy density in the magnetic field also is equal to field square multiplied by a constant, okay? Divided by a constant, that means multiplied by the inverse of that constant, which is also a constant, okay? So in both ways, in both cases, the field energy density in the field is proportional to the field strength square, okay? All right. So let's take a look on the first example of the day, okay? So again, you guys can have a couple minutes to work on this, all right? And then we can take a look at the solution together later, all right? So this one says a solenoid is 1.8 meters long, has 450 turns per meter. What's the cross-sectional area of this solenoid if it stores 0.39 joules of energy when it carries a current of 12 amps, okay? So let me list the nodes here. So we know that the L, the length, is 1.8 meters, okay? We know small n is 450, okay? So because it's 450 per meter, so that means the small n, okay? It's asking you what would be the cross-sectional area, all right? If energy stored in here in the form of B, because this is solenoid, 0.39 joules, okay? The current is equal to 12 amps in the solenoid, okay? So take a look on the equations we had before, and then we can look at this together, okay? All right, so let's take a look here. This is UM sub M here because we use U sub M, okay? But you can use U sub B, that means also means energy by the magnetic field. So previously we know U sub M is equal to, all right, so B square A times L divided by 2 mu naught, okay? So then we are looking for the area. So from here you can see A should be equal to 2 mu naught U sub M divided by B square, sorry, B square times L, all right? We are given this, we are given L, we are not given B, but we can figure out B because for a solenoid, B should be equal to mu naught M times I, right? So we are given M, we are given I, we can take that into there. So replace B with this expression, we would have 2 mu naught capital U divided by mu naught square N square because B is being squared, okay? And then I square times L, okay? So here you can see 1 mu naught here will cancel out the square, so you still have mu naught remaining, okay? But you don't have mu naught on the top. Then you can plug in the numbers you have. So 2 times 0.39 joules, okay? Divided by mu naught is the constant of 4 pi times 10 to the minus 7, okay? I'm going to just leave out the units here because everything is given as in SI units, okay? So then we should be good by leaving the units out, so don't worry about the joules. For small n, it's 450 squared, okay? Current is 12 squared. L is 1.8 meters, all right? So you plug in all these numbers in your calculator, you end up with area equals to 1.18, right, times 10 to the minus 2 meters squared, okay? Should be in SI units because everything is in SI unit, so then the final answer should be in SI unit, okay? All right. Let me know if you have any questions on this one. So if not, then we'll move on. All right. So the next section here talks about an RL circuit, okay, or RL circuits. So basically, this is very similar to a RC circuit, okay. So, but we just replace the capacitor with the inductor, okay. So if you look at the figure over here, then we replace the original. If there's a capacitor here, then it now becomes the inductor, okay. So similarly here, once you put this one, the switch on, so because this is an inductor, so then it has the ability to oppose to the current increase, okay? So then the current will increase gradually through the circuit, okay? So there's a time delay, okay? Although the voltage is been building up on the inductor, but it actually comes build up slowly because there's a opposing factor according to Lenz's law, okay? So mathematically, you can derive that, or for the current. So we can talk about the current here, okay? So it's easier to just talk about the current. So let me just go back one more time. So here, so let's focus on the current because the current will increase from 0 in the circuit, okay? And then it goes up gradually. But for the voltage, actually, for this guy here, the voltage on the resistor, it builds up gradually, okay? But for the voltage on the inductor, it actually decreases gradually, okay? So the correct way to put this should be the voltage on the inductor goes down gradually, okay? It doesn't go up, it goes down, okay? So it starts with the same voltage as this one and then goes gradually decreases to 0, okay? That's what happens, all right? So then when we look at the current in the circuit, okay, it goes up gradually. This is similar to what we have for a capacitor, okay? If you but it's the other way around, okay? So anyway, let's just focus on the expression for this, okay? It's different to the current in the RC circuit, but this is what you should have for the RL circuit, okay? So for an RL circuit, if you put on the switch, then the current in the circuit goes up gradually according to this equation. So then this is exponentially increase, okay? This is similar to the expression for the voltage on the capacitor, okay? But here, we also have this tau constant as time constant, okay? In this time is defined as the inductance divided by R, okay? So it's L divided by R. In the previous case, when you have an RC circuit, all right, it's different as, so for an RL circuit, okay, so let me just put this here. You can take a note here. So for an RL circuit, okay, the time constant tau is equal to L over R. For an RC circuit, okay, the time constant is actually R times C, okay? So these two are different, all right? Okay. So on this one, let's take a look on this example, okay, for an RL circuit. So this one says how much time does it take for the current in an RL circuit with R equal to 130 ohm and L equal to 68 millihenry to reach half its final value, okay. So we are talking about the current. You can use the equation we just learned in the previous slide. So for the current, as a function of time, is equal to epsilon over R, 1 minus exponential to the minus T over tau, okay? Where this is an RL circuit, so tau is equal to L divided by R, all right? Now the question is, we are looking for T, all right? So we have epsilon. No, we don't. Sorry, we don't. We only have L and R, okay? So then, how do we solve for T? We are just given this equation, okay? There's another piece of information. It says that for the time instant that we are looking for, the current is equal to half of its final value, okay? So then what's the final value of the circuit, okay? So final, that means in this case, so if you turn on a switch, okay, so the final value will be, for the current will be when the time is equal to infinity, all right? So I final should be equal to I infinity, okay? T equal to infinity, all right? So then you plug in infinity in the equation. This is epsilon over R, 1 minus e to the minus infinity divided by tau, all right? Now, I think this is a little bit knowledge in the calculus class, but whatever. If you have infinity divided by a constant number, okay, non-zero number, then it also gives you infinity, okay? So then this is equal to epsilon over R, 1 minus e to the minus infinity, okay? E to the minus infinity is 1 over e to the infinity, right? E to the infinity, that should be still equal to infinity, okay? Infinity large number. 1 over infinite number should be equal to 0, okay? So this guy should be equal to 0. So then the final current should be equal to epsilon over R times 1, which is just epsilon over R, okay? So, okay, so then we have this information when at the time instant we are looking for the current is equal to half of the final value, okay? So then I of t is equal to 1/2 omega times R, all right? Now, I times t also equals to omega times R, 1 minus e to the minus t over tau, okay? So then we can set these two equal to each other, all right? So we can set that 1/2 epsilon over R equals to epsilon over R, 1 minus e to the minus t over tau. All right, so we can set it up that way. So e over infinity, or e over R and e over R will cancel out. Okay, so then you have 1/2 here, you have 1 minus e to the minus t over tau. So then this is what you have remaining. 1/2 equals to 1 minus e to the minus T over tau. Okay. Now you have 1/2 here, you have 1 here, so that means this guy should be equal to 1/2, right? Or you can do the algebra, you can rearrange, you can move the terms, move this guy to the other side, move this to the other side. Okay, so move this guy to the side, move this guy to the right. Then in the left, you have e to the minus T over tau. In the right, you have 1 minus 1/2, which is 1/2. Okay, so also tells you this is equal to 1/2. All right. So then after that, we are solving for this T. Okay, so to get rid of exponential, you do natural log for both sides of equation. Okay, so natural log of e to the minus T over tau should be equal to natural log of 1/2. Okay, so then you get rid of exponential, you have minus T over tau equals to natural log of 1/2. So then T is equal to minus tau natural log of 1/2. Okay. Now tau is equal to this guy. Take this expression down here, all the way down here. So then T equals to minus L. You can plug in the numbers now. 68 times 10 to the minus 3 Henry divided by R, 130 ohms. Okay, multiplied by natural log of 1/2. Okay. I'm sorry, wasn't in the camera range. Okay, so then this will give you 0.363 times 10 to the minus 3 second. Okay, this is what you would have. So 0.363 millisecond then. Okay, that should be your time t. So it happens quite quickly. Okay, because probably this tau number is small. It's 10 to the minus 3 over this, so it's very small number. So then it happens quickly. Okay. All right. So this is this one here. Let me pause for a few seconds to see if you guys have questions. Okay, if you have questions, just unmute yourself and then talk to me. Okay. All right. If not, then we'll move on. Okay. So we'll take a look on another example here. Okay. So this one says if you have a circuit like this. All right. So this is a circuit very similar to the lab that we checked last week. Okay, so if we would have done a lab, then this is what we have. Okay, so basically you are going to have like one side of the circuit, it's like you can charge a capacitor. In this case, we are doing an inductor. Okay, in terms of capacitor. So then on this side, you can have current charging network. Okay, on the other side. Okay, so then you have another resistor here. So if you flip this one, you are charging this guy. If you open this one, then you are discharging this guy. Basically, okay, it doesn't look like quite the same, but this is what happens. Okay, basically, let's take a look here. So it says, given the circuit shown in the figure, the inductor has eligible internal resistance and has negligible internal resistance, and the switch has been open for a long time. The switch is now closed. Okay, so if this is being open for a long time, so then anything, if there was any current initial here, should be discharged by this guy already. Okay, for a long time. So the moment you close this one, now you can divide the circuit into two, on this one and then on this one. Okay, on this one, this is just normal. You can cover this side. Okay, on this side, it's just normal resistor connect with a battery, where the battery has, let's assume this is a small resistor here, another one here. Okay, so two resistors in series with a battery. Now on this side, this is a RL circuit. That's where the resistor here, that's this L. Okay, so you close the switch, then the moment you just close the switch, okay, it's asking you A, the moment you just close the switch, what will be the current in the battery, and then in this resistor, and then also in the inductor. Okay, so let's take a look here. So when you just close the switch, we can just look at the two sides of the circuit. Okay, so this is a resistor, this is a switch, there's this battery, there's a small resistor here as well, and then there's this inductor. All right, so if you look at the symbol for resistor and then symbol for inductor, they look somehow similar, but they are different. Okay, so this is zigzag line, this is like curved line. Okay, so curl line like that. Okay, so they look slightly different, but they are similar. So when you are looking at the circuit, you want to pay attention to the details. Okay, so once this is closed, okay, then you can see that the current will go from the positive terminal here, goes through there, and then it will split into two. One goes here, one goes there. Okay, now on this circuit, it's easy to determine. You can just treat this as one circuit. Okay, so the moment you just close it, you can see for the current in the 100 ohms, okay, should be just equal to the epsilon divided by 100 ohms plus 10 ohms, because 100 and the 10 ohms, they are in series with each other. Okay, so then you can see it's 10 divided by 110 ohms. This should be 0.091 amps. Okay, on the 100 ohms. Now let's look at on the other side of the circuit here. We can treat this one as another circuit, because these two are in parallel to each other. So you can just treat them one by another. Okay, it doesn't really matter. Once they are parallel to each other, you can treat one and then treat another. Okay, they are not much related, other than the voltage on them should be the same. Okay, on this side should be the same on this side. Okay, so let's look at on this one. Then this is the RL circuit. Okay, so for the current through the inductor to the 2.0 Henry. Okay, as a time function t, it's going to be epsilon divided by r. In this case, r is the 10. Okay, because just on this side you only have the 10 ohms. Okay, so then r is 10 times 1 minus e to the minus t over tau. Okay, the moment you just close the switch, t is equal to 0, right? Immediately after you open the close the switch, t is equal to 0. So then t is equal to 0 over here. Tau you can calculate, or you can just leave it, because 0 over tau should be still 0. Okay, so e to the minus 0, that should be equal to 1, because e to the any power 0 should be equal to 1. So in the parentheses, then you are doing 1 minus 1. Okay, which gives you 0. All right, so at this time instant, then the current through the inductor should be 0. All right, so let this current being 0, let this current, or you can say this I1, this is I2, being 0.091. So then the current through the battery should be the summation of these two current. Okay, so I on the battery should be the 0.091 plus 0. Okay, 0.091. Okay, so through the inductor is 0, through the resistor, the 100 ohm resistor is 0.091, through the battery is 0.091. Okay. Okay, B, it's asking you long after the switch is closed. Okay, so long time after. So long time after, you can assume that t equal to infinity. All right. So again, we are looking at, let's focus on the left side of the circuit here. So a long time after that, on this RL circuit, okay, we can check on the current. Current when t equal to infinity is equal to the epsilon divided by r, which is 10, okay, times 1 minus e to the minus infinity divided by tau. Infinity divided by tau is still infinity, okay? E to the minus infinity that should be equal to 0. Okay, we have checked this one on the previous example. Okay, because this is equal to 1 over e to the infinity, which is 1 over infinity. That's 0. Okay, so this is 0 then. So then it's just epsilon divided by 10 times 1. Okay, epsilon here is given as 10 volts divided by 10 ohms. Okay, so then it's 1 amp on the inductor. So I on the inductor 2 Henry, that's equal to this guy. Okay, all right. Now, what would be the current going through this resistor? The current I on the 100 ohm resistor, what would be that? Okay, so let's take a look here. Long time after this is open, this is closed. Okay, so then the current I on the left will stabilize. All right, so then there will be no change on the inductor here. So the inductor will not have any opposing effect on the current because current is not changing now. Okay, so then the inductor becomes just a straight line, carries the straight wire, or just a wire, maybe not straight wire, but curved wire, carries current purely. All right, so in this branch, you can see if that's the case, if current is not changing, then there will be no resistance from the coil. All right, so then resistance through this branch is basically 0. So then your circuit kind of becomes like the switch is open, it's closed, okay? And then there's this resistor, there's this resistor 100 ohms, becomes just like that. So on the left-hand side, it's a short circuit, okay? So no resistance at all because the current is not changing, so then inductor doesn't have any opposing effect, all right? So if that's the case, if there's no resistance at all in parallel with this guy, so that means this is being short circuit. So there's nothing going, there will be nothing going through this guy, okay? If that's the case, then current on the resistor should be 0 because the current is kind of lazy. It doesn't like any resistance. If there's a route that has 0 resistance, then it will just all go through that route. Will not go through this guy. Okay, so then this guy has been short circuit, okay, by this wire. So there will be no current going through there. Okay, so then again for the battery, it's going to be again the 100 ohms resistor current plus the 2.0 Henry inductor. So 0 plus 1. It's equal to 1, okay, in this case. All right. Again, I think I'm going this one through rather quickly, but anytime you have question, just unmute yourself and then let me know. I will be addressing your question, okay? But otherwise, I'll just move on. So the part C here is asking you find the current in the battery resistor, 100 ohm resistor and inductor immediately after the switch is open again. Okay, so now this time the switch is open again. Let's see what happens. So if the switch is open again, now it's open. Okay, so this is the switch being open long after it's been closed. Okay, so long after it's been closed, let's list I equal to 1 amps here. Okay, so if this is open, then the current will not go through the battery. Okay, so immediately you will realize because this is open, the current couldn't go through the battery because this is open. So then on the battery, this time, this is going to be 0. Okay. Just when this is open, then the current here doesn't go through that, but then the current will go through this guy here. Okay, so the 1 amps is going to go through this guy. So then on the 100 ohm, it's going to be equal to 1 amps. Okay, on the inductor 2 Henry is also going to be 1 amp. Okay, so you don't have to calculate, you can just analyze the scenario here. So just after this is open, the current is not going through that, so then you have to go to this way. Okay, so then this L and then this this resistor R, the L inductor, they are in series then. Okay, you can just ignore this one. Okay, so then it's just this circuit, the two are in series, so they will share the same current. Okay, of the 1.00 amp, and then on the battery it will be 0 because now this is open. All right, so D then is asking, now after this is open for a long time, what would be the current on all of these three? Okay, so again, because this is open, so on the battery, you still should have the current equal to 0. Okay, now let's look the resistor and the inductor here. Okay, so because there's a resistor here, it will consume energy, right? Because there's current here in the inductor, so then there will be energy stored in the inductor here. But because there's a resistor here, so you'll consume energy. Okay, so you can imagine the as the energy being consumed, because the energy in the inductor is proportional to the current. Okay, or the B field. B field is equal to mu naught Ni. So, but energy is equal to B squared divided by 2 divided by this times AL. Okay, so the area and the length. So then you can see if energy is being consumed, then current should be decreased. Okay, so start to decrease, and then long after you should have consumed all the energy. Then if energy becomes 0, when t is equal to infinity, long time after, then current should be equal to 0. Okay, so then on both of the 2.0 Henry and then the 100 ohm resistor, they should all become 0. Okay, so this is what happens long after. Okay, the energy stored here will be consumed. All right. So on D, again, you don't have to do any calculation, but you can just analyze the scenario, you'll get the answer. Okay. All right. Is that clear to you guys? All right. So, and then if you guys have no question, I think it's about time we just stop here and then come back next time on the next section. Okay. So the next section we'll talk about what's the reactions of the if we have AC circuit. Okay, or we'll be doing AC circuit. Okay. So I'll stop here, and then again, the homework 8 is due tomorrow night. Let me know if you have any questions. We can have a Zoom meeting that I post on the Moodle page. You can click on the office hour Zoom link. We can talk about any questions you have on your homework. Okay. So otherwise, I will see you on Wednesday then. Okay. So bye everyone. Take care.